Section 6.4, Separable differential equations. Just a quick recap, we have solved differential equations that are what we call exact differential equations of the form of dy dx, and the right-hand side is simply some sort of function of x, which hopefully we can anti-differentiate. We have an initial condition, so that enables us to find the plus c, to find then we have our particular solution. But how about a problem where the right-hand side is not all in terms of x, but involves y's as well? What do we do under such circumstances? Well, it turns out for this particular problem, where the right-hand side is x squared times y squared, in other words, the right-hand side happens to be in the form of a function of y times a function of x, it falls into the class of differential equations that's called separable. And separable differential equations can be approached as follows. We can separate the right-hand side by keeping the function of x on the right-hand side, and we can get rid of the function of y by dividing both sides by it, so that it ends up being in the denominator on the left-hand side. And then the next thing we do is apparently something we really shouldn't do, and that is, it looks as though what we're doing is that we're treating dy dx as though it were just a regular fraction with a numerator and denominator that can be taken apart, and the dy stays on the left-hand side, and the dx, which was in the denominator on the left-hand side, ends up then being in the numerator. It's as though we had multiplied both sides by dx. Having done that, the next step is simply just to put in integral signs on both sides. And in fact, if we look at what we've got, the left-hand side will involve a function of y, and we anti-differentiate that with respect to y. And the right-hand side will be all in terms of x's, and we anti-differentiate that with respect to x. Now, this taking apart of dy dx should trouble you a little bit, because remember what dy dx was. We got dy dx from a limit. It was a single unit. It was a limiting form of a quotient, and as such really does not come apart. So there has to be some sort of justification for what we do, and it goes as follows. I start with my dy dx is equal to a function of y times a function of x. And I can certainly rewrite the right-hand side nicely by, let's get rid of my function of y by dividing both sides by f of y, which is the same as multiplying by the reciprocal. And lo and behold, my f of y has ended up on my left-hand side. The next step is I'm going to take integrals on both sides with respect to, which I'm going to write as WRT, with respect to x. So, I've got two equal things. I can simply take the integral of these two equal quantities with respect to the same variable, which is x. So I've got the integral of 1 over f of y dy dx. I've got all that, and I'm taking the integral with respect to x, and then I'm going to do the same thing on the right-hand side with respect to x. All right? The next step that I do is simply to take those blue parentheses and remove them. What does that give me? And now I'm going to look at what I'm going to circle in pink. Remember that when we were doing our u substitutions, we defined the differential du as being du dx times dx. Well, if you can think of, let's just change my u's to y's, dy would be, I'm changing u to y, dy dx dx. And if you look, there is that dy dx dx, and that is the same as dy. So what we have is that the integral of 1 over f of y dy is equal to the integral of g of x dx. So that's the end product that we got, and here it is without the integral signs. So there's a justification that happened without actually having to take my initial dy dx, and it remained as a single unit all the way through. So that's my justification. Let's apply separation of variables to solve for a differential equation. Before we do that, though, a couple of little points about the solution to a differential equation. Obviously, it must satisfy the equation and the initial condition. In other words, if I were to differentiate the y that I get, it should give me what I started with. And the answer will be a differentiable function. Why is it got to be a differentiable function? Because I start with dy dx. It exists, so there is a derivative. And it the domain that I give will be an interval that contains the initial x value. So let's do the example 1. dy dx is equal to the square of xy, and my goodness, that's the same as x squared y squared. So it's a problem that we started off at the very beginning, and I have an initial condition. So I look at this and I think, is this a separable differential equation? In other words, do I have a product of x times the product of a function of x times a function of y? The answer is yes. So I start the process of separating. Remember, the whole point of separating is you want to keep the function of x on the right-hand side, but end up with a function of y on the left-hand side. So I want to get rid of my y squared on the right-hand side, and I can do that by multiplying by its reciprocal. So I get 1 over y squared. It's gone from the right-hand side. And then the rest of it, I have my dy on the left-hand side and dx. I treat that dy dx as though it were a regular fraction, even though it isn't. But the net effect of separation is that it appears to behave like that. Now I'm in a good place to put in my integral signs. So I integrate on the left-hand side with respect to y, and I integrate or anti-differentiate on the right-hand side with respect to x. I probably would want to rewrite the left-hand side as a power function because it makes it a little bit easier to figure out the antiderivative. Antiderivative of y to the negative 2, the exponent, remember I add 1 when I antidifferentiate, so it'll be negative 1, and then I figure out what the coefficient would be. The coefficient is going to have to be negative 1, so that when I check my guess, I'll get my y to the negative 2 after differentiating. Plus a c is equal to anti-differentiate. On the right-hand side, it's 1/3 x cubed plus a c. And, I've got a c on both sides, and they're not necessarily the same c, so I label one a c sub 1 and the other c sub 2. And then I think a little bit more, and I think, you know what? If I have a constant on the left side and a constant on the right-hand side, that's equivalent to just one constant on one side because I could subtract them. So we'll write it as a single constant on one side, and we generally write it on the side where the x is. So let's make a quick note of that we need to write the plus c only on, whoops, that word is on, one side. But please, we must do it immediately once we have removed the integral sign. That plus c must go in at this step. All right, once we've done that, we need to find the value of c using my initial condition. But actually, before we do that, I think we'll rewrite y to the negative 1 back without a negative exponent because most people find it a little easier to work with not with negative exponents. So now let's plug in x is 1, y is 1. The left-hand side is going to be negative 1, and I get 1/3 plus c. So c is equal to negative 4/3. And I now have negative 1 over y is 1/3 x cubed minus 4/3. Now remember what I'm trying to do. I'm trying to solve for y. And I don't want 1 over y or negative 1 over y. I want y equals. So we've got a bit of algebra to do. Let's first of all get rid of the negative sign on the right-hand side. And I've now got the reciprocal of y. So the way to handle this, probably most simply, is to rewrite the right-hand side as a single fraction, which isn't hard. We have a common denominator of 3, and I've got negative x cubed plus 4. Now I've got one fraction equals another fraction, so their reciprocals are equal. And I'm going to write the right-hand side then is 4 minus x cubed. Okay, and you might think you're done, but remember the problem did ask us to say something about the domain, and in fact, if I look at this function, there is a discontinuity. And remember, when there's a discontinuity in my solution, they're going to be more than one branch in of the natural domain. So let's write this down. There's a discontinuity at x equals, it comes from 4 minus x cubed equals 0, x cubed equals 4, x equal the cube root of 4. So then what I'm going to call the natural domain for y. In other words, if you were just given y equals this function and I asked you for your domain, you'd say, oh, it goes from negative infinity to the cube root of 4 union cube root of 4 cube root of 4 to positive infinity, because there's a discontinuity of the cube root of 4. But remember that when y is not just a function that comes out of thin air, it's a solution to a differential equation, I have to restrict my domain to the branch that contains the given point. Now remember, domain is all about x values, so we look at the x value of the given point, which is 1, and I have to decide which branch contains x is 1. Well, if I check on my calculator, the cube root of 4 turns out to be 1.587 union 1.587 to infinity. So which branch will have x equal 1? So it'll be in this branch, the first one. And so I now actually have my final solution. My solution is y equals 3 over 4 minus x cubed with a domain negative infinity to the cube root of 4. We'll go back to an exact value for that. and there is my solution. The rest of the video, we're not going to do more examples. We're just going to do a little practice on solution, practice separating the variables. Remember what we mean by that. If we start off with dy dx is a function of y times a function of x, what are we trying to do? We're trying to get the function of y on the left-hand side with the dy. In this case, we would do it by dividing by the function of y. Keep the function of x on the right-hand side with the dx. So that's what we're going to try and do. So let's look at example A. We're a little short of space. I didn't space this out with enough room to write, but we can still handle it. Remember, we want to get the function of y on the left-hand side. Look at the y. It's in the denominator of the right-hand side. If I want it in the right-hand side, I have to multiply both sides by y. So the y will end up in the numerator on the left side with the dy. The x is just fine where it is. And there's my separation. B is a little trickier. It's a little trickier because we don't even see a function of x. Well, anytime you don't see a function of x or a function of y, it really is lurking there as a 1. So that actually I can rewrite my dy dx as being -1 times cosine squared of y. And now I can do my separation. I'm going to write it above just because I don't quite have enough room. So remember what I'm trying to do. I'm trying to get the function of y on the left-hand side. How do I do that? It's sitting there in the numerator, so I'm going to multiply by 1 over cosine squared y on the left-hand side. And that's going to equal to -1 dx. Right? All right, let's have a look at C. Here is my y. That's the only thing containing y is just that y. How do I get rid of that on the right-hand side? Well, divide both sides by y, or that's the same as multiplying by the reciprocal of y. It doesn't matter which way you refer to it. But I'm going to then end up with 1 over y. That stays with the dy. And then everything else is -3 over root x. That will be times dx. Now, another fine answer would be you could have done 1 over -3y. And then the dy. And then just left 1 over root x dx. That would also be a perfectly fine separation of variables, but actually the first case is the better strategy. And the reason it's the better strategy is because remember where you're headed. You're headed trying to solve for y. So the less kind of extra constants you have attached to the y, probably the easier task is going to be. So usually when there are constants, you keep them with the x term. But it wouldn't be wrong to keep them with the y. All right, let's have a little look at D. My y cubed is sitting in the denominator. Therefore, how do I get rid of it? Oh, easy. Multiply both sides by the y cubed. There's your dy. And then everything else stays the same without the y dx. Getting the hang of these are not so bad. E is a little trickier. In that I've got y plus 5. I've got to keep that y plus 5 together. I don't seem to have a function of x. No problem. Put in a 1. Right? Times 1. So now my y plus 5, I want to get rid of that. How do I do that? Oh, easy. Divide both sides by y plus 5. There's my dy. And then it's just 1 dx. The last problem is a trick problem. When you have x plus y you just can't separate these. You're kind of really stuck. And this is not separable. And you won't be asked to do a problem like that. Okay, and that is it. Ms. Talmashny is going to put together, I hope, a worksheet with just a little bit of practice of separating the variables before we start then the rest of this in class.